What's up, ladies and gentlemen? This is your host, Clay Swackhammer, back at you with another exciting episode of Annotated MATLAB Codes. Today we're going to be doing some image processing. So before we get started, where I'd like to get started is right here in the Food Engineering Lab shared Google Drive and the folder Informal Protocols, which contains some resources for common things that we do in the lab. Then within this folder, let's go to Image Processing and Analysis and take a look at Image Processing Summary. So this should be able to help steer you through the content in this folder. There's really 3 steps and there's a resource for each one. We're going to assume today that we've already taken the images, so we're going to be on step 2, which is going from the raw images to the sizes of particles on those images. And maybe next we'll go on to step 3 in another video. I think I'll break that up. So first of all, let's download test image 1 and 2 and image processing. These are the 3 files that we're going to need. So let's see, we'll make a new folder on the desktop. Okay, great. Alright, looks like I already made, well, no, we'll just put it right on the desktop. Why don't we do that? I want to show you guys how to do this somewhat from scratch so you can do it on your own. We'll extract the content from that folder, extract all. Let's do that. Okay, great. Now we've got a new folder that has our extracted files. Okay, I guess I can't get rid of that for now. So this will be our image processing workspace. So I'm just going to call it workspace for now. And within here, we've got a MATLAB script and then 2 test images. So I've already opened MATLAB, but I don't have any scripts open right now. So let's launch this one. And ignore the crazy color in the editor. That's the same thing as normal MATLAB. I've just changed the colors to look cool. So let's focus in on the user inputs. These are things that you want to change whenever you run this script. So first of all, the file names. Which files do you want to run? Well, test image 1 and test image 2. So you can run as many files at a time as you want. You can do just 1 or you can do 2, that's fine. And the extension right now has to be .jpeg, so that's the type of file that you can run. If you want to change that, feel free. There's a lot of things here you can very easily change to your own needs. Okay, so display output images. That is true if you want to show the images that you've just processed, and false if you don't care to see them. So if you're running batches of dozens of images or hundreds of images, maybe you don't need to print them all to your screen. But if you're doing just 1 or 2, I recommend showing them on the screen. Saving the output images, well, that's just going to save the things that you were shown at the highest possible resolution, and it'll save them in the same folder. So this whole thing does everything out of one folder. It only looks for these images in the same folder where this script is saved, and if you want to save additional outputs, like the output images or the particle areas in an Excel format, it'll do that in the same folder. Okay, so the minimum area is basically saying what is the smallest particle that we'll analyze here. 0.05 millimeters squared is pretty good, but again, you can change that. Okay, crop molt, this basically has to do with how much of the dish we're going to keep in our analysis. If we keep 100% of the dish, that means that we will get some actual, I would say, fake particles. Let me show you what that would look like. These inner ridges right here, this thing, we would be counting those as particles if we set the crop molt to 100. As it turns out, for these larger Petri dishes, as you see here, about 0.85 is good. For the smaller dishes, it's about 0.76. I just recommend keeping that consistent throughout your run if possible. So find dish panel, we're going to leave that as false. That will display a bunch of plots, which would help diagnose an issue with the code if it runs into trouble. And then PMG cal ticks panel is the calibration workspace diagnostic. We'll also leave that to false. We don't care to see that right now. So that pretty much covers it. Those are all the user inputs. Realistically, you only need to change this most of the time. Okay, now we've got test image 1, we've got test image 2. Let's go ahead and run it. Okay, I always hold my breath a little bit. Hopefully it doesn't run into trouble. Alright, now while we're waiting for that, let's just review a couple of the good criteria for images. So first of all, nothing should be overlapping. Particles should not overlap each other. The dish should not overlap or touch the scale. The scale is this L-shaped ruler thing. I also call it the PMG scale for photomacrographic scale, and that's all the same thing. You're just referring to this L-shaped ruler. Now the last thing is you notice how there's a little strip of white on all sides. So may not really look like it because of this weird toolbar on the top, but if you set it as slideshow, you can see how there's white space above this thing too. Okay, so that being said, if you look at this other image, you can see that the scale is hanging off the edge of the image a little bit, and we'll see that it'll deal with that. It won't actually matter, but it's best if you have it all within the field of the image like it is here. And then second, here you notice that the scale is brighter and there's less shadows. So on this other image, you can see there's some shadows, like this long thing right here, which is part of the image stand and one of the turn screws. The scale is darker overall, and it won't matter. But the reason for that is because here the light's pointing from the top to down, so the light's pointing on the dish and the scale were not on, whereas here they were on. These are the ones that I'm referring to as the stage lights in some of these documents. So we want to keep them on if possible. They help reduce things like shadows and make the scale a little easier to see. So that's part of the reason I chose these two example images. But I think they'll both work. I just ran them, so I'm pretty confident they'll both work. Okay, now we've got 3 output images, and they were displayed because we set display output images to true. So they all correspond to this guy, and if we go to our workspace folder, we'll notice that they've also been saved. So we can look at them here, or we can just look at the saved copies of them. Either's fine. One thing that you notice is that we really have 3 different types of output images: the black and white or binary mask, which just is black for particle, white for not a particle. This guy is semi-transparent green, and the advantage of this image is that it allows us to see if we're actually doing a good job capturing the particles. This is really testing the image binarization. So if we're picking up lots of green out here, for instance, where we don't have particles, that would be a green flag, if you will, that this isn't really doing a good job. Now, let me go back to this third one. Okay, it's going to print out all these next output images before I'm ready, but this guy right here shows each particle colored in a slightly different shade. So what that's going to do is tell us if we are counting close by particles as one or as separate. So here you see these guys are close together, but this one's blue and this one's red, and that means they're being counted separately, and that's what we want, because these are really 2 different particles. That's not so much of an issue with that image of the almonds, because it's a very sparse image, meaning there's just not a lot of stuff on the field. But here, we might not really be able to tell too easily whether this guy and this guy are connected. But if we go to the green, or excuse me, the confetti or multicolored image, we can see this guy's yellow and this guy's yellow too, and so they're being counted as just part of the same particle, which could be true. It does kind of look like they're connected. So I have to say I kind of agree with that. All right, now let's just look at these saved files to make sure it all matches up. And it seems like it does, so we're happy with that. Now right here, we can see, for instance, that this guy is being counted all as the same particle, but over here we have some that are close by, but they're being counted separately. Same here, we have this purple one and this yellow one. Now they're only separated by a few pixels, but they are being counted as 2 distinct particles, and I think that looks pretty good. Okay, so we're also going to check the output areas. So the outputs of this script are going to be the areas of the particles, and then a little header that'll have the image names. So let's open that up. Now this, you notice, is a funny Excel icon. It's because it's actually a CSV or comma separated value workbook which is kind of a nice archival data format. It's good for sharing with people that might be on a different version of Excel. A downside is that you can't do a lot of the fancy Excel formatting, but you can open it in Excel and such. I think it's a good platform for this use. Okay, so this is test image 1 and test image 2. Test image 1, I think that was the almonds. Let's see, yep, that was the almonds. Okay, great. So this is going to be particle areas in millimeters squared. And it looks like it found 42 particles. And you know, that seems like a lot, right? Wow, I mean, there were only maybe, I don't know, 5 or 6 large ones on that image. So sometimes I like to check the binary mask and then check this green image and see if it really looks like there could be 42. And you know, I think there could be. There's a lot of these small fragments here. There's really only 4 or 5, though, that are large. So let's see if we can find 1, 2, 3, 4. Okay, around 5 that are large. So that appears to be doing a pretty good job. I'm happy with that. Now, test image 2 was a lot more dense. We had a lot more stuff going on, a lot more stuff in the field. So I mean, I'm expecting several hundred particles out of that. Of course, I just ran this a few minutes ago, so I already know what the answer should be, or will be, rather. And it's going to look like we have 412 particles. It goes down to 414 with the headers too. Okay, so now once you have the particle areas in this format, you could share it with people that don't have MATLAB. You could do any kind of analysis you want, post it to your Facebook, put it on your Instagram, share it with your grandmother, and you wouldn't even need to share the raw images at that point to do analysis on the particle areas. So this is just kind of another checkpoint. Now if I put in 10 images, they would be right across the top, 3, 4, 5, so on and so forth, and the particle areas listed in each column. If you want more of this stuff, perimeters of particles, the shape factors, you can easily add that to the output and save it as well. But I think most people are interested just in the particle areas, so that's what I have it set up to save right now. There's not a lot of information on here that's kind of extra or to confuse you. I think that's kind of a good thing. Okay, let me see, does that cover it for the output areas? Oh, yes. So for the workflow for this whole thing, you know, how should I actually run this with my images? The way I think I would do it is if I had 3 or 4 images at a certain time point, I would run those together. And then this document will have 4 vectors, 4 column vectors of particles, 1 for each image at that time point. And then if you wanted to, you could copy paste that into the master document or something like that, or you could just save it with its own name, call it, you know, time 30 minutes or something. That would be just fine too. All right, well, I think that covers it for image processing. So generally, image processing is what we call taking some images and making some new images or some processed images, and that's what we did. And we've saved those right here, these 3 and these 3. Next, maybe we'll do a little image analysis, and that's what we might do by taking some output areas and then coming up with some values like Rosen-Ramler or X50 or so on and so forth. It'd be easy to interpret. Okay, so hopefully that's cleared up any confusion about image processing. Feel free to send me a message. I think I put my contact information on here if you have any questions. All right, this was your host, Clay Swackhammer, coming at you with another exciting episode of Annotated MATLAB Codes.